Okay, so in a previous mini lecture, we learned that a force causes an acceleration. A push or a pull causes an object to change its motion. In this mini lecture, we're going to take that one step further, and we're going to look at how all the forces acting on an object might influence its motion. So we're going to define the idea of a net force. The net force acting on an object is taking all of the forces that are interacting with that object, all of the pushes and pulls, regardless of where they're coming from, all of them acting on that one object and adding them together, which sounds pretty straightforward, but we have to be careful. So first, let's define that. So the net force is the sum of all the forces acting on an object. Sum, adding up. But what we want to be careful about is that we recognize that force is a vector. So, in the previous example, we talked about how if I wanted to move this eraser, if I wanted to change its motion, making it go from stationary to moving, that I would cause a force, a push or a pull. Let's say in that direction. I would change the motion in that direction. Could also change the motion in that direction, or that direction, or that direction. So even though the change in motion might be similar in all cases, I get it to go a certain speed, the direction is important. So we want to keep in mind that forces are vectors. And so adding them together requires us to do that vector algebra, and we'll do some practice with that when we look at the net force in specific detail. So why is net force important? Let's imagine for a second that we have an object. And you know me, I'm not that great at drawing. So there's my object. Let's say it's an apple. And I'm going to apply a force to that apple in the rightward direction of a certain magnitude, a certain strength. Well, because I've applied a force in that direction, that apple might change its motion in that direction. All right, well, how does that change in motion look? What is it affected by? Well, what if instead of that force applied to the apple, I apply a larger force, represented by the longer arrow? If I increase my force acting on that apple, what happens to the motion? Does it look the same? Well, it's both heading in that direction. It's both speeding up. So it's having an acceleration. Remember, forces cause, accelerations cause changes in motion. But how do the changes in motion compare? Well, a bigger apple is going to have a bigger force is going to cause a larger acceleration. If I push harder on something, I'm going to get it to change its motion in a bigger way. So as I increase the force, I increase the acceleration for a given object. Okay, so that's one relationship. This tells us that the force is proportional. There's our sign for proportional to the acceleration. What's another influence? What if, instead of changing the force, I change the size of the apple? And by size, I don't mean physical size. I mean I make it more massive. So we'll call this apple little m, and we'll call this apple big M, capital M. It's more massive. It's heavier. It's got more stuff involved. How does that affect the motion? So in both cases, I'm now going to apply the same force. So my two representations of forces are the same. But what happens to the motion of the little apple in mass compared to the big apple in mass? Well, how does increasing the mass influence the acceleration? Boy, when I'm pushing on something little versus pushing on something big, getting it to change its motion, the bigger thing, sure takes a lot longer time. It's slower. Increasing the mass decreases that acceleration. What does that tell us? That tells us that the mass is inversely proportional to the acceleration. When the mass goes up, the acceleration goes down. Now this is important. Remember, in this case, I kept the same apple, so mass was the same. In this case, I kept the same force, so force is the same. happens if I want to achieve the same acceleration for a given object? So if I want to maintain my acceleration so that the little apple has a certain change in its motion, I want that big apple to have that same change in motion. What do I got to do? Well, I got to push it harder. If I want to get a change in motion that's equivalent to this little apple with that force, I got to give my big apple a bigger force. So as I increase my mass, in order to achieve that same acceleration, I have to increase my force. Well, what does that tell us? That tells us that the force and the mass are proportional. Now, Isaac Newton, he's the one who sort of figured all this stuff out, at least framed it appropriately. Galileo had something to do with these ideas of motion as well. But how did he take these ideas, these relationships, and put them together and to look at how is the force impacting the acceleration for a given mass? Or how is the acceleration impacted when I change the mass? Or how is the force necessary, what I need, going to be impacted if I change the mass, if I'm trying to achieve the same thing? He put these ideas together into Newton's second law. Newton's second law tells us these relationships. It tells us, here's Newton's second law, that the force is equal to the mass times the acceleration. For a given mass, if I put a force on that mass, I'll get a certain acceleration. If I change the force, I'm going to get a bigger acceleration. If I have a certain force and I change the mass, my acceleration is going to go down. This one goes up, that one goes down. So Newton put together this idea of how forces influence an object's motion. There's one caveat. Newton's second law applies to the net force on that mass m. So not just a single force, but if we're going to truly encompass Newton's second law and its intent, it is the sum, the net force. And we represent that net with the capital sigma, the indication of sum, the sum of the forces. So it's the sum of the forces that cause an object's acceleration. Now we said that it's very, very important to remember that forces are vectors. What about mass? Is mass a vector? Nope. It's a scalar quantity. It just gives a property. It doesn't really have direction. What about acceleration? Yeah, acceleration did have direction. Remember, we worked with that direction of the acceleration for an object that's motion is changing. I want you to recognize that because of this relationship, one of the things that we can hang our hat on is that the direction of the force and the direction of the acceleration are the same. And again, this is the acceleration of the object as a result of the net force, all of the forces acting. So, if an object is moving to the right, and I apply a net force to the right, object's moving to the right, and I apply a net force to the right, the object is going to start speeding up. The acceleration is also to the right. Rightward motion, rightward acceleration, the object speeds up. If an object's moving to the right and I apply a force in the other direction, I'm slowing it down. I'm bringing it to a stop. The force is to the left, which means the acceleration is to the left. If the motion is to the right and the acceleration is to the left, the object slows down. And you can go back and do those ideas, thinking about how the force comes into play with the acceleration. The net force is always the same as the acceleration. Direction. It's always the same. All right, I'm going to stop there on this little mini lecture, and then we're going to look more carefully in the next one on what do we mean by net force and how does it come into play when we're looking at an object's change in motion. The example that we gave to develop this had a single force. Why is it important that we don't just look at this in terms of a single force when an object might have lots of forces acting on it? And it's really the net force that comes into play. All right, good job.